So we'll be doing intro to optimization, and this is a very, very interesting topic because that's basically how your neural network is going to learn. And you want your neural network to learn quickly, and you want it to learn fast and well, basically. So we'll first start with Kahoot. So get your phones out, get whatever devices out, because we're going to get started with a Kahoot right now. Can join the Kahoot right here. We'll give everyone like a minute to join. Okay. Just a notice, if you get top 3 in the Kahoot, you can make progress towards a very nice Discord role. And at the top of those roles is Kahoot Grandmaster. So that's an incentive to attend our workshops and learn more about like AI. So we'll get started. I'll give everyone like 1 more minute maybe for everyone to join. We have 11 people, so we have about like 19 people. So let's see. I'm still expecting like maybe five or six more people. If you want to join the Kahoot, just reminder there's an incentive. The Discord roles have very nice colors. We'll start at 6:08 sharp. I'll just close the sign in for the Kahoot at 6:08 sharp. So right now, once it's 6:08, I'll just assume everyone who wants to participate in the Kahoot has already signed up. Okay, so it's 6:08. I'm gonna close it in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, we're gonna get started now. So let's get started. What is gradient descent? Okay. Let's go to the next question. Okay. So next question. What is backpropagation? Yes, it is a recursive method of computing gradients. It does not compute a neural network output. That's not backpropagation. So, all right. Next, why do we need backpropagation? All right, so it's actually calculating the gradient update. So calculating a loss function is different from calculating the gradient of the loss function. And technically, it doesn't make the neural network run faster. It's only to help us train the neural network. Oops, I clicked too fast, but sure. True, false. We can calculate the gradient of the first and last layer of a neural network at the exact same time. There's only two possible answers. You have a 50% chance of getting this right. Okay, so basically backpropagation, you have to start from the last layer and you have to backpropagate all the way to the first layer. So you cannot calculate both of them at the same time. You need to know the gradients of the last layer and you need to pass it all the way back to the front. So they can't be done at the same time. Okay, let's actually see the scoreboard. Okay, next. What is an example of a loss function? Okay, looks like everyone got this right. Yeah, you know this, and CE is actually cross entropy. Okay, backpropagation occurs during which step? So there's multiple stages when you're doing machine learning, when dealing with a neural network. What step do we see backpropagation occur? Yeah, it's during training because backpropagation is when we're computing gradients to update the weights of the network, and that's done during the training phase. We do not during testing or evaluation or validation. All right. Okay. And this is the last true or false. No extra memory is used during backpropagation. True or false? Yeah, it's false because we actually do have to use memory to actually store the gradients of each neuron because we need to send it back. We need to send it back to the first layer. So let's see who's first. I mean, who's third. So third is all right. So we have Cameron at number 1, how to reverse list at number 2, and number 1 please at number 3. Okay, so put your you can DM like me Stone on Discord with your Discord ID. Oh yeah, and we'll start getting on those ranks for y'all. Okay, so this is let's see. Every question was answered correctly by most players. That sounds good. So okay, let's get back to the workshop. So what's the agenda for today? The agenda today is primary optimization. So we have a neural network. How do we improve it? We'll teach you a little bit about about overfitting and underfitting data. We'll tell you about we'll tell you about tuning hyperparameters and how that can help with the optimization of a neural network. We'll teach you about a little bit about regularization and what it can do for generalizing a network. We'll also talk briefly about weight initialization, different optimizers, and some challenges that you might face in optimizing neural networks. So I think I'll hand this over to Jason, who gets started. But first, we'll get started with the first question. It's just that how can we improve the neural networks we talked about in the last workshop? So we use backpropagation. Uh, so as you can see, actually, what do you think? What does everyone think? Like, so we can do backprop. We can update the weights of the neural network. Like, how do we make it better? Okay, so I see one E there, and then I'll just wait for like a few more seconds. Well, actually, it's E. So you can feature engineer your data. So that means that you can select features from a data set and you can run your network through that. So instead of training on unnecessary or useless information, it has only the relevant data that's required to make the decision or prediction. You can generalize your model. This is something that we'll cover a bit briefly in optimization. And yeah, we want ideally a better prediction accuracy and better hyperparameters. So let's talk about the train test split. Jason?
Sure. So up until now, we haven't really talked about the data set much. But basically, when you're training a model, you're training on some data set, right? For example, there's a data set called MNIST, which is just a collection of handwritten digits. There's another data set called CFAR, which is just a bunch of random objects. And so, yeah, data is everything. But it turns out that the way we use our data during training can make all the difference when it comes to improving our model. And so the first thing to note is that we usually split our data set into a few different components. On this slide, we just talk about what is called the training set, or the training component of our data set, and then the testing part of our data set. And so, oh, I wasn't finished yet. Sorry. So why do we want to split our data set, even just between these two things? Why do we want to split into training and testing? Well, you could sort of think of it like this way, right? So if, for example, you wanted to evaluate how well your model is doing, right? And you're training it on, say, your training data. And let's say you don't have any test data, it's just a bunch of, your entire data set is just training, right? If you wanted to evaluate how good your model is actually doing, how would you do that, right? Well, you need to test it on some data, like you need to give it a quiz, right? Or just show a bunch of, images if you're using an image classifier, and then say, okay, how much did you get right? The problem with using just a training data set is that your model has already seen this data before, right? Like it basically, in a way, has sort of already memorized the answer, right? So if you're testing it on your training data set, you're sort of only testing how well it can actually remember some data, not how well it actually learned the distinct characteristics of your data set, right? And so we need to care about this thing called generalization, right? Which happens when you're testing it, not on your training set, but on data that it's never seen before during testing, right? So this is like an actual real test of questions that it's never been exposed to before. And that is a much better way to evaluate your model. And usually we split the data set into 80% training and then 20% testing. So I think for, so for example, like if you have a data set of 100,000 images, then 80,000 of those under the split would go to training and 20,000 would be used during testing. Next slide, please. So here we talk about an issue called overfitting and also underfitting. We mentioned that generalization is something that we want to test in our model, right? Generalization being how well does it perform on data that it hasn't seen, right? A real test of how good it is. And so what happens is that you end up having these two different sets of metrics, right? One is how well am I performing on my training set? For example, while I'm training, I see that, maybe it gets 98% accuracy currently on my training set, right? But when we're testing, we see maybe it has only like 60% on the data it hasn't seen, right? So we have like these two different sets of metrics, right? We report two different accuracies. A problem arises though, which is fairly common, when we have a really high accuracy on our training data, but not as high of accuracy on our test data, right? So the example I gave, like 98% on your training set, it might sound very good, but again, remember, for actual performance of a model, we want to look at the test set only, right? For judging generalization, right? So if we look at our testing set and it gets like 50%, then that's like, not very good at all, right? So what happens in this scenario, we have some images here, is that if your training set, for example, on the left side, you see this blue curve that is very curvy. And you also have this black curve, which is just a straight line. And then you have all these data points that are these little black points on your graph. You can think of the black points as sort of like your data set, right? And then the blue and black line as two different models that we're comparing, right? One is a lot better than the other. And it might not be what you think, right? So in the blue model, we have something that very accurately captures actually every single data point, right? And so, we might say that, well, in this case, wow, we got like 100% accuracy on our training data set. That might seem nice, but when you actually go to a test data set, for example, to points it hasn't seen before, so you can imagine like adding a couple more points. Let's see if I can get like drawing options. Okay, how to draw? Oh yeah, thanks, Joseph. I can't find where to draw. But yeah, like pretend like now these yellow points are your testing data set, right? Points it hasn't seen before. So now we can assess generalization. Now we have errors, right? Now our blue curve isn't capturing those yellow points, right? And so maybe our accuracy, at this point on our test set is 0%. It's not capturing any points, right? Versus like black line, sorry, instead of 0%, I'm going to correct myself and say it's just not as good as we'd hope to, right? So yeah, there's a very big error on some of these points, right? And ideally, we want those kind of bars that he's drawing to be as small as possible, right? And then if you compare it to the black line, right, we would actually say it's better, right? Because if you look at the distance between the black line and those yellow points, they're actually much closer than, some of the points for when you're looking at the blue curve, right? And so what we say is that the black line would fit the data better, right? Or it actually generalizes to unseen data a lot more. And the reason why is because it doesn't, what we would say, overfit the data, right? Overfitting meaning, well, as you can see right here, it's very carefully, too carefully captures every single data point, such that, if you give it a new data point it hasn't seen before, it's like, whoa, what is that, right? Like I've basically only memorized every specific point in my training set, right? So you're a little bit too careful about these fine details, and not thinking more broadly as a model, like what are these features that I should be learning, right? That apply to things that, I haven't seen before. And in the second image here, we sort of have the same thing, right? So in the green model, you have a data that you have a model that's overfit, right? So it's learned very precise peculiarities about your data set, but not really about, really precise peculiarities about the items, like specific items in your data set, in your training data set, but not about like the just overall general characteristics of, the entire data set, which would be captured better by the black line, right? So hopefully the overfitting concept and why it's really bad is pretty clear. So there's a question, could you say that overfitting is when you fit to the noise more than the underlying signal? Yes, that is precisely what it is. You care more about those very fine details, that noise, rather than, just the overall idea of what you're supposed to be learning, right? Which is maybe, what digits look like or what dogs versus cats look like. And the noise could be like specific dogs and specific cats. Okay, next slide, please. And so in this slide, we introduce a third split into our data set, right? So we had training, we had testing, and now we're introducing a third split in our data set called the validation set. So again, like we started this workshop with the question, how do we actually improve, training our models? How do we get better models? And, like one of the answers in that little quiz at the start was we could tune some hyperparameters, right? So in gradient descent, you could change a couple of things, right? You could change, for example, the step size, or what we would call the learning rate. And you could also change, for example, the direction that you're actually stepping in. But also when it comes to your data, you can, change what we'll look at soon is called batch size. Yeah, of course, your architecture, you can change some things with that, add more layers or more units or whatever, right? But so naturally another question arises like, well, okay, I have all these knobs that I can turn, right? Learning rate, maybe dial it up a bit, batch size, pick a specific number, architecture, maybe try some random stuff. But how do I actually fairly pick a set of hyperparameters so that I really know that my model is going to generalize very well, right? And so could we tune our hyperparameters by looking at how our model is performing on our training set? Well, obviously no, because for the same reason that we don't want to, assess generalization, for the same reason why we have like a test set, right? Like looking towards our training set gives us no clue about how our model actually generalizes, how well our model actually generalizes to unseen data, right? So looking at our training set is not a very good idea if we want to pick some better hyperparameters to improve generalization. But should we use our test set to tune our hyperparameters, right? That seems like a better option because, well, the whole reason why we have a test set is so that we can assess generalization, right? And the answer is also no, because you could think of it this way, right? If you're looking, so you can think of your test data set as sort of like maybe a quiz you're taking in class, right? And if you're looking at this quiz and you're saying, maybe next time I should study a little bit more for this thing, right? And then you take the same quiz again and you do a little better. Well, I mean, you basically cheated, right? So yeah, you shouldn't also look at the test set to change your hyperparameters to improve generalization, right? And so that motivates a third split called your validation set. And this validation set, the sole purpose of it is so that you have a set that's not used at testing time that you can use to tune your hyperparameters, right? So that there's no cheating going on when you finally do evaluate at test time. And typically our split, it can vary, but an example split is 60-20-20. So 60% for training, 20% for validation, and 20% for testing. I've also seen 80-10-10. So 80% for training and 10 for the others. But really, you can also sort of play around with the splits that go on. And you might get some variation with your performance there. Next slide, please. So it looks like here we have like a little question here. So how do we fix overfitting? And this sort of segues to our next section. But yeah, here are the answers, and I guess I can go over each of them. So how do we fix overfitting? If you remember, overfitting happens when our model is too complex and has memorized too many particular details about specific images in our data set, right? It's paying attention to the noise and not the underlying signal, as was suggested by David. And so how do we actually fix it, right? Actually, could we go back to the previous slide? So here are some really broad ideas, right? And the first idea is to reduce your model complexity, right? So if you have like a lot of layers, a lot of neurons, that's a very complicated model, right? And so it allows you to have very high capacity to do, very curvy, very specific fine-tuned models. But again, as we saw earlier, that might not be what you want. And so you can sort of simplify your model a bit to prevent it from being able to get to that specific level. D, penalize large weights, we'll actually see, I think next, can also help with overfitting. So penalizing large weights. Let's talk a little bit more about that. So there's this technique called regularization. And there's actually two versions, or two common versions of regularization. One is called L1 regularization, and the other is called L2 regularization. Both of them penalize your model for having very large weights. And so, for example, what that looks like here with L2 regularization is that when we're training, we have our loss function. And one term, I mean, the term that you've already seen is, your loss function, for example, mean squared error for linear regression, or maybe cross entropy for more, complicated problems. With regularization, we actually add a term to our loss function, right? What we call a regularization term. And here on the left, you see the regularization term we add. At its core, it's penalizing for, in this case, the square of the weights. But really, the idea is that if our weights are big, our loss is going to be big. And remember, our goal is to minimize the loss. So what happens is that now we're searching for a model that it's not only fits our data well, but also has small weights, right? And so the idea with why we would want to do something like this, maybe Joseph can add on to this, but from my understanding is that you're basically going to reduce your model from having very large slopes, for example, right? Like, for example, what we saw with the really, like that blue curve in the overfitting slide, you saw that it kind of jumped around and went crazy and had a very, very particular, fit to the actual, the data set, right? If we penalize for weights, then the idea overall is that that's less likely to happen, right? We have a more flat, more smooth model. And in turn, something that looks more like that straight black line, right? So that's sort of my take on it. Did you want to add on to that, Joseph?
Yeah, another way you can think about it is that when you're computing gradient descent or you're doing backpropagation, you're effectively forgetting part of the original weight. So you can think of it sort of like let's think of like a very small scale example. For example, let's say you have 10 images and one of the images has like this specific pole that you think is important for the classification. And so and maybe you weight that pole by some value. But maybe that pole only appears in one of the 10 images. So the idea of regularization is that because the pole isn't important, if the pole was important, it should appear in all 10 images. But because the pole is not that important for example, classification, for example. So over time, as you train on the other examples, you'll eventually forget the pole and start to remember more important features that appear across the whole training data set. And with this kind of regularization, the idea is that now you're focusing on features that actually occur across the data set rather than just like very specific details that maybe like a small subset of the data set has.
So there's another question. How is L2 term used in backprop? And that's actually the very next slide. So it's a very nice segue. So basically, when you're performing gradient descent, right, you need to take the gradient of our loss function, right, with respect to all our parameters so that we know how to update each parameter. And now that we have this new regularization term in there, we also have to compute the gradient with respect to that, right? Because it's a sum, right? The gradient of a sum is just the sum of gradients. And so we can think about taking a gradient of just the term alone, right? And then adding that to our normal gradient. So here on the left side, you see the regularization term, right? That's what we added to our, what we added to our loss function. And if you take a gradient of that, you can sort of see, like, if you took it with respect to the weight, the squared would come down, it would cancel with the 2 under the lambda, and then you would have something that's like the sum of a bunch of weights, right? And if you took it with respect to bias, then, well, your regularization term doesn't care about bias, it just becomes 0, right? So your gradient would just be, have a bunch of, would just be a sum of a bunch of weights. And yeah, I think we're done with this slide. Specified, a lot of regularization methods. So yeah, so there might be a bunch of other approaches out there that have been developed to help achieve the same effect with regularization. Dropout is a term that appears, but yeah, there's many different techniques to solve this overfitting, encouraging generalization problem. And yeah, regularization, as we saw on the previous slide, is just one of them. So yeah, our goal here is just to sort of give you a sample of what's out there. But from now, I think Joseph will take over and talk about different optimizers.
Yep. So we'll get started on optimizers. So basically now we know about backprop. So let's think about like different ways we can actually like update the weights because with the gradients. So there's actually a lot of optimizers, and you might look at this and you're like, well, there's a lot of equations. The good thing is that they're already like pre-implemented in most machine learning libraries. So you're not going to be dealing with the math from scratch. But it's still good to understand. It's still good to understand why they work and how they work, so that you know which one is the best for your particular task, because each of them have their strengths and weaknesses. So let's start with gradient descent. Actually, we call it batch gradient descent because the idea is this: we're gonna take the training data, we're gonna pass it through the neural network, we're gonna calculate the gradients for all the possible with respect to all the possible training data, and we're gonna batch it all up into us, and we update it all at once. And so that's batch gradient descent. And you can already kind of see, like, if you have a really huge data set, terabytes of data, that's not physically possible, because that means that you have to squeeze terabytes of like gradient. Squeeze terabytes of like data before you can actually update your model, and that's not tractable. So how do you improve of that? So first, this is just a kind of like an idea of how gradient descent works. So basically, you would evaluate the gradient, and then you would just update by subtracting the gradient time scaled by some learning rate. And usually the learning rate, I think, is on the order of magnitude of maybe like the highest is probably like maybe point 0.1, 0.2, but usually people can go quite low to like 10 to the negative 5. But it depends on the task, basically. This is learning rate is a hyperparameter that has to be tuned. So, well, that's a sort of modification. It's like, why instead of updating all the gradients at once, why don't you just update the gradients a batch at a time? And so what we can do is actually you can randomly slice the data set into mini batches. And this adds an extra hyperparameter to the plan, which is the mini batch size, because that every time you update the model, you update the model by only the examples from that mini batch. So what you do is you pick a mini batch for every epoch, and then you update it with gradient descent once, and then you repeat it until you've used all the remaining mini batches. And this is better in the sense that now you're saving memory, and it can be a bit faster, especially because you now can yeah. So I think an implementation of this would be you shuffle the data, and then after that you batch the data, and basically do standard gradient descent, but instead of training on the whole data, you train on the small batches. You update on the small batches basically for until all the batches have been used, then you move to the next epoch, which is basically a one training cycle, by the way. So then that's we are sort of like building up here. So like we talked about batch mini batch gradient descent. So now let's talk about stochastic gradient descent. So stochastic gradient descent, actually the batch size is just one. And basically the idea is that it's still the same. You shuffle, and you randomly pick an example, and then you update it with that single example. And the idea is that because you're picking it randomly, and you're not using the same sequence of training examples at the time, the idea is that it should help the model generalize a little bit better, and like get out of local minima a little bit better, because you're sort of like you're agitating the weights a bit more compared to like a very structured like sequential gradient update. And technically a stochastic gradient descent is also technically done in mini batch gradient descent, as mentioned before, because we actually do still randomly shuffle. We usually call that variant a stochastic mini batch gradient descent. So both work. The reason why you want to use mini batch is because you want at least as much set training samples as you can fit in the data, as you can fit in your memory, I mean. So that's pretty, like, that's good for training a model faster. So this is an example of stochastic gradient descent, and it's basically the same thing, except now you're just taking a single example at a time. So I kind of already like touched upon it while I was explaining the different types of gradient descent, but the idea is that you can see that stochastic gradient descent and mini mesh gradient descent, they sort of like have a very like tortured path towards the minima, which is the red dot in the center. Because the idea is that you want to minimize our loss function, right? So we need the minimum possible loss, which translates to the highest possible like performance. So you can see the stochastic gradient descent, it doesn't follow a straight line. It sort of like jumps around randomly, because each training example is just a little bit different, and because we're picking the examples randomly, it's not going to always hit in the same direction every time. So the good thing about this is that when we have many local minima and we want to keep searching for better minima, then stochastic gradient descent and mini batch gradient descent, because there's a bit of randomness involved, we can jump out of that. But sometimes, you can see, for example, stochastic gradient descent. Another issue is that, you see it's jumping all around. It's taking a lot longer. You can sort of like intuitively see there's a lot more errors required to reach the minima, compared to, say, like batch gradient descent, which just like makes a beeline straight for the minima. So because the idea is that, you want to train your model quickly, and you want to and you want to get out of, you want to deal with the local minima issue, especially when you have many local minima. So now we think about different ways we can actually improve on that and actually head towards the objective while getting our local minima. So here's another optimizer you can do. You can do momentum, which is a stochastic gradient descent momentum. So the idea is sort of like, you can think of it like rolling down a hill, for example. So the idea is that when you roll down the hill, you're gathering momentum, right? And maybe there's like bumps on that hill, but you're still kind of moving in the general direction, which is downwards. So the idea of momentum is this sort of idea that, you sort of aggregate the previous gradients. And because the idea is that sort of like there's a certain direction you're heading, right? So you're going to keep a running aggregate of the previous gradients, which is basically the previous direction, a history of the previous directions you're headed, and you sort of like head a bit in the direction while you're also heading in the direction of steepest descent at your current point. And this idea is sort of so that you accelerate to the local minima. So like you can see, for example, SGD like fluctuates a lot without momentum, but with momentum, it still fluctuates, so it still has an opportunity to break out local minima, but still it takes less iterations to head towards the minima. And yeah, so it dampens this oscillating behavior. For SGD, you do not need to store the momentum of every parameter in memory. So the way it works is that sort of like you create a running sum. You create a running sum because yeah, you basically create a running sum of the previous gradients, and then you add the new gradient multiplied by a hyperparameter, as you can see here. Because if you look right here, I can dive deep into the terms a bit. If you look right here, vt plus 1 implicitly encodes vt minus 2, vt minus 3 times gamma. So in effect, actually, you don't really need to store. You don't need to keep storing. You don't need to keep storing every single past update, because it's already self-calculated in there. And let me just clear the drawings. And let's keep moving on. So like, well, momentum's sort of good, but there's actually a sort of a slightly better variation, which is SGD with momentum and acceleration. So this is you might know it as Nesterov. Some people call it SGD with Nesterov acceleration. Cameron, so effectively you're just storing an extra term. It's just a one extra parameter. You're not storing a running history, so you're not actually storing like a list of all the previous gradients, but you're storing like you just need to store the previous gradient update. Yeah, you just need to store the previous gradient update, and then you just multiply that by a hyperparameter gamma to weight how strongly you want the the direction of the previous gradient to matter in your next update. And mathematically, you can see as we run it recursively, it keeps a running history. You can show mathematically it keeps a running history of all the previous gradients. Where am I? So like for the Nesterov acceleration method, what you can think about is effectively it's sort of a different concept. It's that instead of because you can see in the previous one, what happened was that we take a we take the previous gradient. I mean, take the previous gradient, we scale it by some value, uh, and then we add it to the gradient update. Here is something slightly different. The idea is that we first move in the direction of the previous gradient by a little bit, and then we calculate the gradient of that particular function. So another way to think about it, it's sort of like we are calculating the gradient at a different point from where we originally are in the direction of the previous gradient. And the idea is that this sort of helps the convergence a little better. So if you actually run the math a bit, you the Nesterov method actually has like theoretical guarantees for like a certain class of functions where it will actually converge a lot better, and it actually generalizes empirically. Like if you do a neural network optimization empirically, we see that the Nesterov acceleration method also does give some improved performance in convergence to the minima. So it's sort of like a different modification. That momentum still involved, but the idea is that you take a step first before you start calculating all your gradients. And this picture sort of like tries to attempt to explain that. So like we we take a jump, and then we calculate the gradient. And the idea is that now once we calculate the gradient and we move in the direction of that gradient, you see that we are actually now moving the green line. So actually we are moving a lot further than if we were to do momentum, which is just the blue line, which is just basically we take a gradient update, and then we move in the direction of the previous gradient. So uh, that's basically sort of like now, okay, so we have momentum. So like, how can we do better? So this is this concept of like, technically, your learning rate actually doesn't have to be a fixed value. You could make the learning rate a function of other things. And the idea is that for example, at the grad, for example, it basically modifies the learning rate based on the gradient. That's like a function where it actually like sort of modifies it based on the gradient. So it tries to make you take the optimal step based on the size of the gradient. And that's sort of like an issue where like the gradients, because you have to keep a running like sort of like sum of the gradients in a way, because it will keep accumulating as you keep going on. Eventually, like the learning rate will like the denominator will blow up, as you can see here. The denominator g is the gradient here. It's going to blow up, and then eventually your learning rate is just going to go so small that it stops learning basically, because you're basically multiplying by nearly zero. So that's undergrad. And you can see things like undergrad. We have gradient descent and undergrad, and you can see undergrad just makes a beeline for the optimal. While you can see gradient descent will first end up in the saddle point before it actually converges to the minimum. So like sort of this, yeah, undergrad sort of like make sure the update is like scales correctly to the gradient that you calculated. So you're always getting the optimal calculation. Yeah, you're getting the optimal descent basically towards the optimal. You have eta delta, and eta delta is just sort of like a proposed fix to the disappearing learning rate issue. So as you can see here, I'm just gradually building up, because that actually at the end of it, you'll see that after like basically after trying to quash like the various issues with different optimizers, we'll eventually get to something that we actually use. So RMS prop is it does something different. So RMS prop actually also a different way of tuning the learning rate. And so the idea here now is that we want this idea of momentum. We also want this idea of like because sometimes if you have too high learning rate, you overstep. So you can imagine, like, for example, if you're like taking steps, right? If you're walking down the staircase, if you took like one step at a time, you'd be able to easily walk down the steps. But like if you took like you walk like 5 steps at a time, you're gonna just fall down. And it's kind of like similar-ish analogy. This idea that if you overshoot it, you're not going to get the optimal descent. So RMS prop is sort of a different way. You don't really know too much of the details. I Because usually RMS prop and all these other optimizers, you can easily like find off-the-shelf implementations in all of your favorite machine learning libraries. But anyways, that's not the main one that we use. You can see RMS prop also is sort of like improves upon, and it's slightly better than undergrad for like convergence. Uh, the one, yeah, this is the meat. So like, if there's anything you want to take away from this workshop, well, Adam is sort of like the golden standard at the moment. Because Adam right now, yeah, Adam is sort of like the golden standard. It's a very good general purpose. It's sort of like it sort of takes in the best of both worlds. It takes in some tricks from RMS prop. It takes some tricks from Ada delta, and there's for each parameter there's adaptive learning rates for like almost everything, and because they're all adaptive, then now you're actually getting like the optimal sort of like your some of your hyperparameters become functions of themselves basically. So now they're all as optimal as mathematically can be, well, in this particular context. And in this and so basically Adam right now I think is usually one of the most common optimizers you'll see in like most machine learning applications. I think SGD with stochastic gradient descent with Nesterov acceleration sometimes is also used for like very particular domain areas, but Adam is an all-around general purpose pretty good optimizer. So if we compare all the optimizers we've talked so far, you can see that Adam's just like the best in general in like optimizing, because you can see, for example, Elder Delta actually trains fast, but you can see it's not really reaching the optimal quickly compared to Adam, where it just hits the optimum quickly compared to everything else, which is stuck in the saddle point. Every other method is stuck in the saddle point. So just some final thoughts about optimizers. Technically speaking, all the methods I suggested would work would work in like to varying degrees, I guess. They'll find a minima, but we don't want to just find the minimum. We want to find the minimum as quickly as we can and as the best minimum that we can. So basically we want to find it as accurately as we can. So SGD is okay, for example, but SGD is sort of like there's a lot of because we are not really because we are jumping all over the place. For example, SGD does not necessarily converge quickly. Adagrad is used for sparse data, but Adam is the sort of like the general purpose well, I wouldn't say golden standard, but it's a very good general purpose optimizer for like most of your applications. So if you're training neural networks, like maybe like eight out of 10 times you'd be using Adam. And then the other 2 out of 10 times is if you have like a very specific domain that has like a slightly better optimizer. Like if you tune technically if you tune SGD really well and you add a few stuff to it, you could outperform Adam in some limited cases, like I think convolutional neural networks. Some of them might perform better with SGD, but Adam is just general purpose. You almost can't go wrong with it. And there's also optimizers that are not based on backpropagation. So like there's different other ways of optimization. Gradient descent is sort of like the most computer friendly version because gradient descent there's you can parallelize it. It's computationally cheap per iteration to calculate the gradient. You can do things like genetic algorithms. You can do things like second order methods like Newton-Raphson optimization methods. But all of those either require a lot of computational powers or a computational power to like compute, or maybe for some of them it's sort of like it's not very computer friendly. So it might be a technique you use to solve like some equations, but it's not something you can just easily run off a computer. And that's the last sort of like one more. We are going to sort of like moving on to the next section of our workshop, which is how do we initialize on neural networks. So this is quite important because your initialization will actually affect what local what you can converge to and how fast you can converge to. So actually, let's think about it. So what happens if you set we give you here like a neural network, I think. So what happens if you initialize the weights to 0 here, and we want to update? So like what happens if if you initialize it to 0, you'll actually see if you do calculate is that the output is 0. So for no matter what input you put, so like there's nothing that's going to be updated to your gradient descent. And because there's nothing that's going to be updated to your gradient descent, then doing backprop, so then you're not going to get anything useful. Your model's not going to learn, and that's so. Usually, we usually don't initialize weights for 0. So if you initialize with the same random value, that you get something similar issue where like it'll be a bit more deterministic. You have a similar issue. The hidden layer is going to converge to some value, and it might just get stuck there. And yeah, and that's also not optimal because you want to be able to explore. You want to be able to explore the function and find a very good local minima, or ideally the global minima. So actually, we can initialize weights with random values. So random values usually we have to keep in track. Basically, usually we initialize it with respect to a normal distribution. So if you remember, like if you know a little bit about statistics, normal distribution is like that bell curve and we usually do it with the mean centered around 0, so the average centered around 0, and with a certain variance. So the variance tells the variance sort of like describes like the probability of how far like a data point can be from 0 when the mean from how far the data point can be from average. So we usually initialize it with a certain variance, because if we initialize if for example too small a variance, so then everything's going to be close to 0, what happens is that when we update, eventually the gradients is going to go to 0, and then you're not going to learn much. But if you initialize the weights to like too high, then the output will explode, because when you have high weight, when you have high weight, so you multiply the input, you're going to get very large values, and then eventually it's also going to reach a similar issue where it's going to just stop learning, if you look at it mathematically, because then random values like works a lot better, because now you have like a random assortment of like you're sort of like starting at a random position in the loss function, and you can actually start calculating gradient updates that matter. So this is actually sort of like the issue. We cannot have too high or too low, too small gradients. So usually we control this with gradients. I mean, we control this with variance. Sorry, we control this with variance. And yeah, we can. I will just talk like very briefly about different kinds of initializations or the bias. But bias actually technically can initialize as 0, because bias just effectively shifts the output of the input data. And usually during training, the bias is a little bit less sensitive compared to like the bulk of the weight initialization. Yeah, so I think that's pretty much it for our optimization workshop. Thanks for coming. If you have any questions, feel free to hang around. Me and Jason are free to answer any questions.
We also have some resources on the next slide, in case you were interested.
Yeah, we also have like we actually do have like a momentum visualizer for those that are still here. If you are interested in, let's actually show you. So actually, there's this website. It's really cool. You can actually see how momentum works. You can try and play with the momentum variable, the momentum hyperparameter, and see how, if you have high momentum versus low momentum, what happens to a high step size? Oh no, you see, look, if I increase the steps, wait, if I increase the step size, oh my goodness, look at this. It's like a mess. And then if I lower the step size, oh, this is good. And you can see if I have too low a step size, you can see it doesn't converge to optimum, the solution so far. So you need a good balance where, like, you reach the optimum like right here, but you also want a correct momentum, so you reach the solution very quickly. So if you have too low if your momentum multiplier is too low, you'll see that it's sort of like doesn't reach it quickly. But you want it high. You want it just like a sweet spot right here. So there's a lot of tools here, and there's sort of like a mathematical treatment of like the stuff we talked about in this workshop. If you're very interested in the math, they have a lot of fancy widgets you can play with. They actually like delve into like the eigenvalues and things like that. You can also see things like I think this is the talking about fitting, I think. This actually visualizes the fitting process. And they talk about momentum. They have a lot of widgets, a lot of mathematical things you can look at. And yeah, it's optimization is a lot of math. If you're interested in like learning more about optimization, you have classes like Math 173 A and B by Professor Saab. He does optimization, and you'll basically learn what we just taught in this workshop, but like more mathematical treatment of it. And in deep learning classes, in deep learning, you'll also learn sort of like a bit more higher level, but like implementation based. Like you get to mess with gradient descent, and you have some exposure to it. So yeah, this is the workshop. Thanks everyone for coming. If you have any questions, let us know.
Thank you, everyone.